Welcome to Intelligent Electrical Power Grids Week 1, Lecture 1. Today we will talk about the power system over time and how it evolves right now. The learning objectives of today is to see the challenge and the roadblocks in achieving a 100% renewable grid. The power system, as it is right now, has a rather simple structure. There is a generation side, producing electricity. Then we usually step up the voltage via transformers for a high voltage transmission grid to transport electricity over entire countries. Once it reaches its destination, a city or an industry, we step it down again for distribution to the consumers. Transmission topologies are usually given in these one-line diagrams as seen here in the right. Arrows are loads and circles are generators. But the grid is changing, and we will talk about different ways of modeling, describing, and visualizing them during this lecture. In modern grids, loads, such as electric vehicles, might even appear and disappear, and maybe topologies change more often due to more frequent switching actions. But let's talk first about renewable energy in general. If you look at traditional generation, it's typically fossil fuel based, so it costs money. You have to pay for the fuel. Fossil generators are environmentally not friendly. They have CO2 and other emissions. But at least they do what you want. You can control them as you like, and they are very stable. Renewables, on the other side, are for free. The primary energy carriers, wind and solar radiation, cost nothing. You just have to pick it up, collect it somehow. They are also environmentally friendly, there are no emissions, and they are even renewable. That means wind and solar will come again tomorrow, next year, and so on. So they are, when it comes to long-term availability, actually pretty reliable. However, they don't do what you want. You cannot ramp up the sun or the wind if you need more of them. Additionally, renewable sources are connected to the grid via power electronics. Such inverter-based resources, unfortunately, do not intrinsically contribute to the stability of the grid, such as rotating generators do. When you want a 100% renewable power system, you will face a couple of roadblocks, a couple of challenges that you have to take care of. First, you will need a lot of tech upgrades. For instance, the power flow that is normally unidirectional from the generation side to the load side becomes potentially bidirectional. This means that power flows back and forth. This will require upgrades with the transformers, with the protection system, and so forth. Second, you need flexibility. That relates to the fact that renewable generation is weather dependent and variable. You might need some storage, you might need flexible loads, maybe also flexible generation to counteract the fluctuations from the renewable generators. Everything needs to be more agile because of the renewable infeed. Line loading is another challenge. The power system was originally designed for street lighting and later also other things, but electric vehicles, electric heating, and electrified industry are a new quality of loading. We are consuming much more than originally planned. The power lines come to their thermal limits and need to be upgraded. Sometimes we also have voltage problems. So suppose a long electric feeder, maybe a long street in your village, connected with a transformer. The further away you are from that transformer, the voltage will decrease. In-feed of renewable energy for instance, rooftop photovoltaic panels, might lift the voltage at that particular location. So it was easy to calculate and dimension it if you only have loads on a feeder. But the moment you have prosumers and bidirectional smart charging and photovoltaic panels, this gets much more complicated. Another challenge is lack of inertia. Inertia is connected to the second problem item of the previous slide, stability. The rotating masses of the old, reliable but dirty generation units, synchronous generators, are replaced with fast and low inertia generation units using power electronic converters. By that, stability decreases. Resilience is another topic. The moment something happens, something breaks, or you have an outage, you have blackouts, or maybe a cyber attack, how serious will it be? How do you withstand the first shock? How do you prepare up front? How do you restore operations? We call it black start. And it's not made easier with renewable energy sources. And finally, we also have to look at the cost. Although renewable sources have a compelling cost aspect, you remember the primary fuel, sun and wind, is free, they still require investments. And it's sometimes easier to delay and squeeze out the business case of existing infrastructure before you invest in something new. But the renewables are not the only troublemakers. Not only troublemakers are used smartly, they even are able to solve system problems. This example shows a frequency collapse, a stability issue. Something happened. Maybe there is a loss of a generation unit or something broke in the system. In this case, the frequency collapses. And it even crosses a certain lower limit of 59.5 Hertz here. This would trigger a cascade of other problems. More generators would disconnect, and we might end up in a national blackout. The green curve shows the normal frequency excursion without any smart helpers. The two other curves can be achieved if renewable generators help. In this case, it's wind. If the wind farm is a smart wind farm, it will react to this emergency situation and offer stability services. In this case, it's power dispatch and using its limited but still available kinetic energy. Both are made available with smart controls. Today, we had a look at the power system at large. It's a certain grid, a network of assets for generation, transmission, distribution, consumption, typically visualized in these one-line diagrams. And we discussed the challenges you need to face if you want to replace fossil generation with renewable generation. They are all solvable. Most of them are of technical nature, and that can be fixed.